Hi, I'm Jeff Yarger. I'm a professor of chemistry, biochemistry, and physics at Arizona State University. Today we're looking at Project 2, the handout I provide for Chem 343 ASU-Online students, which is physical chemistry laboratory. Now, ASU-Online provides a unique challenge for laboratories. And the general concept that we use in physical chemistry can be summarized by calling it PChem Cloud Lab, which is we're doing things where we are trying to use remote access, automation, and to be able to access kind of a modern modality for laboratory experiments. And this is specifically relevant in physical chemistry, where more and more of advanced instrumentation and molecular spectroscopy and thermodynamic measurements, etc., can be made using remotely accessible equipment, where you have control of it because these are typically highly automated and highly computer-controlled type systems. So the first part of my handout, which is available at biopchem.education for the general public, and it will always be available on Canvas or the LMS at ASU for the students in the course. This one is specifically describing for fall 2021. And I start by just giving a little bit of an overview of how this contextually relates at ASU, the laboratory, to some of the online lecture courses, because really the laboratory courses are meant to enhance the lecture courses in the same subject matter, in this case physical chemistry. And specifically what we're looking at here is molecular thermodynamics. And we're getting into the heart of kind of chemical and physical thermodynamic processes at the molecular level, or with molecules. So our laboratory are designed as projects because all of these have kind of a computational component, a remote or cloud experimental component, and then it takes the data from both of those and has an extensive data science or data and error analysis component as well. And I really think of those three sections as making up an overall project. So for Project 2, we're really getting into the heart of chemical and biochemical thermodynamics. And my introduction is not meant to give an extensive background, but more provide a lot of the citations needed to look up any of this material of both the computational, experimental, and data science background components to this. In this case, some of the thermochemistry background, where I give quite a few references where students can find more information on this. And this is really just meant to summarize that. So I provide the figures show kind of some of the major experimental components. One is constant volume calorimetry. The other is differential scanning calorimeter. And I show the one that's available here at Arizona State University for remote access. So like we said, we call this often PChem Cloud Lab, which is mostly remote or online. And typically we start these projects at the computational. So students have access to computing resources, the research clusters at Arizona State University, where they can do research level ab initio quantum chemistry calculations. And the details are provided in this handout of how to access these systems and what type of calculations are relevant for this project. And so I specifically in figure 3 show an example of looking at this case at benzoic acid and the GUI interface that's available to doing some of these computational experiments, where you can really get an idea for the thermochemistry, the enthalpies, the energies associated with some of the processes we're looking at, or some of, for example, the heat of formation, purely computational, before we then move on to the remote experimental. Now, constant volume, or affectionately called bomb calorimetry, is something that is hard to do in kind of an automated remote setting, but this is something that can be done through ASU Sync, where you're interacting with a teaching assistant or an instructor that's running it remotely for you, or something we can do in kind of a simulation mode. And then differential scanning calorimetry, which is a very commonly used form of calorimetry in both academics and industry, in the chemical industry, biochemistry, etc., is something we do have remotely accessible, where it has automated processing, where you can change in samples and run this calorimeter remotely or online to collect data for this project. And then finally, you're going to take that and both the computational data and experimental data, and put it together, analyze it, process the data, analyze it, relate it theoretically, relate the computational to the experiment, relate all of that to known literature values, make sure things are calibrated well. How does it relate to theoretical concepts in molecular thermodynamics and what you're doing in a physical chemistry course, in your lecture component of the course, etc. And then finally, as mentioned, an important part are the references, which are mainly cited in the introduction for not only the common textbooks that you're using in the lecture portion, but quite a few other what I consider important or curated references and citations for any of the background material you would need for this. If there's an area in either the computational, experimental data analysis that you need to brush up on, or you want more background on, it's typically provided in these references. So hopefully this gives you a brief overview of the handout we use to introduce the projects for Physical Chemistry Laboratory, the ASU Online edition. And please enjoy this project and others in the series for this course. Thank you.